Could you please upload that?
I have uploaded actually. Just go and check on Imparters.
I'll check again because one of the students recently told me that they wanted it to be there.
Yes, yes.
Yeah, it's available.
Okay, so let's start. So I welcome you all to the first session of our lab CLP301. Normally we organize this actually lab in our fluid mechanics and heat transfer lab. But because of the COVID, actually we are not able to run that lab. So what we have decided that if we can run that online, that lab. So overall objective of actually this lab work is not just, so you have already actually gone through different courses of fluid mechanics and heat transfer, right? So you already know all the fundamentals. So that's not a question. But when we talk about, right, you guys will go out actually. So after 2 year or 3 year, you will be in some industry. But whatever these fundamentals or whatever you have learned, right, you have to use it in some practical application. So just actually this lab work is in that direction, one step towards understanding these machinery or whatever fundamentals we have learned, how to use them to address some of the what is called main problems in the industry. So like if you want to pump a water, simple example, right, to some tank. So you know the fluid mechanics and what is the procedure, how you can pump, right? You can solve all the equation, even though you can come up with the design that how much actually plumbing you require, what are the different fittings you may require, what are the different valves you may require, what kind of pump you need, right? All those things. But that is the theoretical part. So when you have to design, then you have to go and buy, you have to choose all those things, how that pump looks like and how what are different kind of fittings and what are different kind of valves and you may require, and you have to put actually where. And the biggest question is how. Once you put that thing, then what is your prediction? How means you have designed with certain calculation, right? Whether you can get actually those calculations right or not. So to address all those issues, we have this kind of lab. So we have actually like a 4 experiment for fluid mechanics and 4 experiment of heat transfer. So I have already shared the list. In that list, you have your faculty advisor name, your what is called lab person name. So today we have actually for this experiment, Reynolds experiment and the force vortex. Today we have with us Mr. Mukesh. So he has prepared the video, whatever you have gone through on imparters. And also we have actually 2 TS with us. So Simran is there and Atmika is there, right? So if you have any question, you can write to me. You can also contact TS and also you can contact Mukesh regarding this experiment, right? For next experiment, which is cell and heat tube exchanger, for that actually we have different person from our lab and different TS. Right? So just you can go through that list what I have shared. You will find out that who is in charge of that experiment. So what is called motive behind today's session? As you know, actually we have combined all the groups together, and Ashutosh have shared already that actually subgroup information with me. So each subgroup has to submit one report. The link will be created on the Moodle, right? So report number 1 with actually experiment number 1. So you can go and upload your report by next week. So next week we will start the same session for this cell and tube heat exchanger. Before that, you have to submit all the reports, or all the reports means all the subgroup has to submit their reports by 2 p.m. Right? Just try to stick the deadlines. Otherwise, it's a very difficult, right? So that's a humble request to you that just submit your reports on time. Don't delay them. What I have done also, I have actually uploaded on Moodle one sample report. So just use that as an example. Don't try to like copy and other things. we will come to know eventually. So just use as an example, as a reference, so you can just prepare the report. That's the one of the like good report I could find, but that is not the best report. So you have to actually what is called, don't just actually, you can make it better than that report as well, right? So next time if I have to share, then I can share one of your report with that. So let's start. Any question? Whatever we have discussed till now. If there is no question, then let's move for this doubt clearing session. So today, actually, in the session, we are going to discuss two experiments. One is the Reynolds experiment, and second one is the force vortex, right? So you have already studied these means both the what is called experiment, or I will say fundamental and basic of these two actually experiment in your fluid mechanics course. So first we can discuss about the Reynolds experiment. So I assume actually you all of you have gone through the video that I have uploaded on Imparters. So how many have you gone through that video? Ashutosh?
Yes, sir.
Okay, Hemant, you have one question, right?
No, sir, I don't have question. You were
You have
asking
raised
and
the hand.
I have gone through. So you were asking now whether I have gone through or not the video. So I
Okay,
was
okay,
just
great,
looking at
great. Okay, that's fine. So I assume, yeah, you have gone through. So if you have gone through that experiment, then if you have any doubt, so I am here right now. Simran is there, Atmika and Mukesh. So you can ask actually any doubt that you have.
Sir, we have one request for the videos that they just do the experiment part, but they don't explain why they are doing this. So, what I could observe, at least in both the videos so far, for the first experiment, that the the person who was doing it was just doing what he did, but why that was being done was not illustrated. So, before reading the manual, we didn't have any idea about that. So, could that also be covered in the video, please?
We have to update the video, but what we can do actually, we should look at the feasibility also, right? So they have to again repeat the experiment, so that won't be a good idea. What we can do,
Sir, can I? So,
yeah. So let me finish, then you can, right? So what we can do, that why we are actually interested in performing that experiment, we can discuss in our what is called these doubt session, right? Is that okay?
Pardon me,
Yes,
sir.
sir, it's totally fine.
Right? The overall objective is actually that if you have any doubt or anything, it should be get clear, right? Then how, that's a different issue. So now next question someone is was asking, right? So you can
Sorry.
raise actually, if you have doubt, just you can raise, there is an option, right?
sir, I had a question just
Yeah,
about policy, sir. So this, sir, does this attendance session have like a like that? Is it necessary that we attend this session, or only if we have doubts?
I will say you attend it. It's not, sometime it's not actually you having doubt. It's also important what actually doubt others have, right? And what's the solution or what's the answer for that. So it's a learning
Yes.
what is called session. Already what I have done, I have actually reduced your load, right? So you don't need to just go, each group has to present at different sections. So right now in just one what is called 2 hour session, we can interact and we can actually just ask whatever question we have, right? So at least actually if you can't spare at least what is called 2 hours or 1.5 hour depending on our doubt clearing session, then it is not right. So it's
Yes.
yeah, so that you can do in what is called offline lab session. You have to present there, I think, for 4 hours, right? And there this attendance policy is very strict. So at least online you should means I assume you should be what is called available for this doubt session, right? Okay,
Yes,
so I assume no one has doubt about any experiment.
Sir, I had a doubt.
Okay, good. So raise your hand so I exactly know actually who is asking. Huh? Okay, so Vishruta. Okay, yeah.
So, sir, I was wondering that in the experiment, the video that we saw, the readings were not complete. So, how exactly are we supposed to get the rest of the readings?
Okay. So there are two things, Vishruta. First thing, you are right actually. Although means I have seen that video, there are few readings actually. If you carefully see those videos, there are few readings, so you can use them. What other thing you can do? You can also simulate actually these experiments. So you will be developing a model. Let's assume if we are talking about the Reynolds, what is called this Reynolds experiment, right? So what is our objective? Our objective is to find out the laminar to turbulent transition, right? Now, if we look at the basic, actually, what is called understanding of these two flows, the laminar and turbulent. So laminar flow is very well structured, right? Highly predictable flow. So how we actually what is called perform experiment, and how experimentally we know that any flow is stable or laminar, you can say, right? What do? You put some dye stream there. And if you are seeing actually your dye stream is just going straight in the flow, that is laminar. And if you are putting dye stream and it is just breaking up, right? There is a lot of cardiac motion. So that means your flow is no longer laminar. That's the first observation, right? You can't say now my flow is actually turbulent. That is not true. First thing is actually if the dye stream is just going fluctuating and just what is called breaking up, then you can say no longer my flow is laminar. Now still you increase the Reynolds number, right? So how you can reduce increase the Reynolds number? If you see what is the what is called definition of Reynolds number, inertial versus viscous forces. You can put that thing. And what are the what is called these parameters there? You have velocity, means the flow velocity is there, dimension of your tube, that's a diameter, and what is there? Viscosity is there, so dB, and the density is there. So now you see what are the parameter, those are constant in that Reynolds number calculation. So first thing is the density of the fluid is constant, that you can't change, right? Dimension of the that actually tube is constant, that you can't change because you have fixed setup. Viscosity you can't change. So if you can't change actually these three parameters, what's the parameter left? That's the flow velocity, right? So flow velocity, how you can change? Now you have actually at the inlet flow rate. So you are increasing the flow rate. And now you can ask actually one thing, that I'm increasing the flow rate, then how my velocity is actually increasing or decreasing? So how you get that actually velocity, or that's the average flow velocity, right? So you take the flow rate, you divide it by that flow rate by the cross section of the tube, and then you will get the average velocity, right? So that is the way. So now you know the basic behind this experiment. So what you can do, you have few readings. You can also simulate using your parameters. Let's say that you have written one code, or in one Excel you have actually put all the readings. Now you will put different flow rate, and then you will see actually that how the flow is increasing and how the flow characteristic, means it's a laminar and turbulent flow, that is increasing. Now question you may ask, that while performing the experiment, I can visualize the thing, whether my dye stream is actually going straight or is a fluctuating and breaking up. But mathematically, how I can do? So what you can do, you can plot actually the graph, that is friction factor versus Reynolds number. So at least for laminar flow, what you can do, you can calculate for the given actually system that how my friction factor in laminar region is varying with the flow rate, or indirectly with the Reynolds number. So what you should get that linear relationship. That is actually based on your what is called that this dimension you are taking, whether fairing friction factor or friction factor. you will get 16 by RE or 64 by RE, right? So all those what is called observation you can put in the report. And few data points you already have from what? From these experiments. So you can overlap them. And then you can look at actually how good that fit is. Right? Normally what happens, these experimental reading, right? What we have, they have certain error because of actually there are a lot of pump is running, right? If you have put this experiment, maybe some vibrations are there and human error also. Suppose that I'm measuring the flow rate, right? So I have certain error in measuring flow rate also. So that also means what is called lead to certain error in the experimental observation, right? So, but that's fine. But the trend should be same as what we have learned in our courses, right? So, is that means answer your question?
Oh, yes, sir.
Right? I expect one thing from you also. Means this is for all of you. These are very simple experiments. So you are at your home, and if you want to suppose that you want to design the same experiment, how can you do? And I assume you all have mobile phone with the camera, not old Nokia phone, but is a smartphone. So everyone has this camera. So if you actually you can perform some experiment. Let's take one actually this glass tube or maybe whatever tube you have pipe, right? You can connect to the tap and just you can actually rotate that knob. So you are increasing the flow rate. And if you can put some dye stream there using some needle or it's just actually the blue ink you can use, right? And you can perform that experiment. That will be really great. And then based on your observation that okay, that you can measure. So how are you going to measure the flow rate? You can have some what is called one glass is there. Let's say it's a 200 ml. You can just take actually stopwatch that is in your mobile. You can calculate that how much time it is actually taking to fill that glass, right? So let's say the 200 ml is getting filled in like 20 seconds. So from that, actually, what you can do, you can calculate the flow rate. And based on then you can see that actually when the dye is breaking up. So it's a very simple experiment. So if you can run at home this kind of experiment, that's completely fine. But the safety is one thing. Only simple experiment, not like very what is called that heat transfer experiment you want to run. Please don't do that thing. But if some basic experiment you can run, that's completely fine. So that will actually means that kind of experiment if you can run at home and you can put in the report, that will be really great. So that will help you to understand the concept of the fluid mechanics, and also it will help you in designing the experiment, right? Normally what we do, we come in the lab here, experiment is ready and everything, just we are taking ready, but that's not the challenging part. The challenging part is if I'm asking you to design some experiment, right? Then you have to actually what is called put all the what is called learning, whatever you have learned and all your innovation together to design something in a way that it is the replica of exact experiment what has been done. So if you just read about this actually the origin of this Reynolds experiment, this Reynolds experiment was actually performed by Oswald Reynolds in I think 1883, right? So 1883, that's 100 years, so approximate 80. So 130 or 140 years back, right? That time there was no fancy watch, no smartphone, even the cameras were not there, right? So what that guy did, he actually what is called designed this experiment, took a glass tube, even the pumps were not there. So he designed a what is called tank. In that tank, he was maintaining some water level, and due to gravitational actually what is called head, the water was flowing, and he was putting some ink. So there was no camera that you can capture. So what this guy was doing, he was observing the oscillation of that dye carefully, and it was surprising, but he observed that holds true till now. Now we have a lot of technology, lot of equipments, right? So that's the beauty of experiment. If you are correct, then you will get the correct reading and your observation will be like rock solid, right? Any other question?
Sir, am I audible?
Yeah, Meghna.
Yeah, yes, sir. Sir, regarding the simulator part, is there any particular simulator do we have to use, like either Excel or MATLAB is fine?
It completely depends on you. You are free to choose anything. If you want to simulate these experiments, so two things are there. As I said, you can simulate using actually what is called this mathematical or tool or software, whatever. So there are so many, right? One can do use Excel, one can use actually Mathematica, one can use MATLAB, one can use what is called ANSYS, COMSOL. These are the software available. One can use Python also, right? And now I see many people, they are interested actually in the machine learning. So I will be happy if you can use machine learning to predict certain behavior. All right? But just
Yes.
try to put everything, yeah. So you are free. But
Yes,
our
sir.
objective should be same. I should not predict something else actually. I should only focus actually what is my objective. And I have to build everything around that objective, right?
Yes, sir. And the simulation part is compulsory, sir. Is it compulsory?
No. It's not actually compulsory, but it's up to you. You have been given means enough freedom, so you can just come up with any idea, whatever you like, right? So as I said, you can design at home. Just you can take a plexiglass tube, you can put something, you can what is called capture this dye stream breakup with your cell phone, and then you can say, okay, I performed this thing, and my what is called I got the transition at 1800. Normally, whatever we have studied that the transition takes place around 2100 for the in case of tube, cylindrical tube, right? But now if I ask actually means is true that you will get this transition around 2100? So what will you say? Anyone, any guess?
The flow would be turbulent, sir. Is it?
So 2100, it's not called a complete turbulent. It's a transition, right? So what happens? It once this flow wants to be turbulent, but there is not enough energy there. So then it will come back to the laminar, right? So you will see this kind of vibration in the dye stream. But still you will increase further the Reynolds number of the flow rate, assuming the other parameters are constant. Then you will see that there is a complete breakup of the dye, right? And then, so with normal camera, actually you can see the breakup, but you can't actually capture the what is called the structure of these actually breakup, right? So we have studied in turbulence, there are these eddy formation, and then there is energy cascading. These bigger eddies, they actually get smaller and smaller, and they dissipate the energy, right? At the level where the energy has to be dissipated using these viscous dissipation. So, but that you can't see. But what you can see with normal this camera, those have like 25 frames per second they can capture. You can see that dye stream is no longer actually as a filament. It is breaking up, right? So that's fine. If you want to see those structures, then you have to literally like go to like 10 to 20,000 frames per second. You are not actually on campus, but if sometimes you come back, I will show you with a high speed that how these structures evolve. But you have to picture them with a high speed camera, means like 20,000 frames per second. So we have special cameras actually in our labs to capture actually these phenomena of these hydrodynamics, right? So that is the thing. But it's about your what is called imagination and innovation, whatever you can put. You have enough tool around. Just how you want to perform that thing, that's up to you.
Yes, sir. Sir, and also apart from the experimental values that have been given in the video, do we be provided with any other experimental values, sir? So I think there were only 3 values that were provided in the video for the Reynolds number experiment.
Okay, so because actually you have to submit this report by next week, this one, right? So I means I will actually request you whatever you have, please stick to that and try to make report out of that. But I will take actually your suggestion, and I will what is called ask actually our lab people to work on that if they can provide actually more reading for our next experiment onwards. Is that okay?
Yes, sir. Yes, sir. So till now onwards, it is better to follow the 3 readings that I've given for the Reynolds
Right,
number.
right, right. Because if I ask, right, the 1 week will be over. We don't have that much time, right? But good
Yes.
suggestion. Yeah.
Yes, sir. And also the simulation part is our choice, no, sir. It's not compulsory.
Yeah, it's not, but you should put, right. So you should put something. It's like asking actually that I have come to your home and I'm a bit hungry, right? So I need a food, right? Somebody can give me pizza, okay, that's fine. Somebody can give me aloo paratha, all those things. So it's your choice, but you have to come up with something and report. You can't just leave that thing, right? So that option is not there. Yes, you can put actually, you can do some simulation, that's fine. You can do certain calculation also, that mathematically I have derived that thing, that's also completely fine. If someone has actually, there is open what is called this open form and other software, if they want to use, that's also fine. But something has to be there on report that shows that you have put enough effort to understand this system and to utilize your know-how actually about this system, right?
Yes, sir. Got it, sir. Thank you.
So I had a doubt.
Yes.
Sir, regarding the experimental setup, in the course plan, it was mentioned that we can use the one which is given in the lab manual. But
Right.
can we use like other images? Like if we find some images online, so can we use them if we cite them? Or can we
Yeah.
make our own images?
Of course, actually means you are free to use those images. But two things are always keep in mind. First thing is that if you're coming up with your own idea, right, it's perfectly fine, you can use. But if you are taking certain images and certain information from what is called with these wave sources, right, and I'm including the literature as well. So one thing I missed actually, so let me include that thing. Means in this experiment you can also do certain kind of literature survey. So suppose that what is the progress has been made, right, in this field, laminar to turbulent transition. You can take some paper, you can put the analysis, you can include in the report. That's completely fine. So even the literature survey also you can include in that, right? So now we will come back to, yeah, if you are taking some information and some what is called images from the web portal, you have to mention the reference always, right? Otherwise actually
Yes,
it's a
sir.
big issue. Yeah. So if you are taking, please mention that I have taken this image from this link, right? Or I have
Sure, sir.
taken this image from this paper, right? So that has to be included in your references.
Sure, sir.
Any other doubt?
Hello, sir.
Yes, carry on.
Sir, in the fourth vortex experiment, in the theory part where we have to derive the velocity and the surface profile of the fluid,
Right.
what will be the boundary condition in deriving the velocity profile? Like one of the boundary condition I can think is that at r is equal to capital, the angular velocity will be omega.
Right.
And what will be the second boundary condition?
Yeah. So my friend, that you have to drive, right? That's why that question is posed to you.
No, the derivation I can do. I'm just asking the second boundary condition.
That also you have to find out. Right?
Sir, I have something. Can I share with you that?
So I can give you one just what is called. So we have studied. We have studied in rigid body motion, right, in fluid mechanics.
Yes, sir.
Just go back and actually just read those concepts. You will
So
find.
that is for surface profile. And for velocity profile, we have to use Navier-Stokes equation. So for solving those equations, we need two boundary conditions.
So
One of,
outside you have to take that actually what is called this angular velocity. That's the only one.
yeah, that is one boundary condition. The second, I need another one.
Second,
Is
you have
it
to
at r is equal to 0,
at the
v is equal
center,
to
right?
0? At r is equal to 0, v theta will be 0.
Yes, yes. You can take that thing.
Okay, sir. Thank you.
But this experiment is about getting that profile. Is
Yes,
that
sir.
right?
But in the theory, it is written that we have to derive velocity profile as well.
Okay, okay. You can just look at. Any other question? So I assume now no question. You have understood everything in those videos, right? Because today you can ask. When there will be viva or presentation, then we will be asking you all the questions, right? So if there is no question, then we should close the session. Aman, Amber. Babya, you don't have any question?
Hello, sir.
Yeah.
So can you please explain how should we go about the error analysis?
Okay. So error analysis, how you do, right? So let's assume that you are getting actually what is called this friction factor, right? You are calculating. So let's take the example of what is called this Reynolds experiment, right? So what we do, the simplest thing, we calculate this friction factor and we plot against the Reynolds number, right? So in actually, if you see what is called when we have derived these equations for the friction factor, we'll put the pressure, what is called pressure difference between inlet and outlet, right, of the tube. So we will put that thing, we know the flow rate. So what we will get exactly those points. They will fall on this 16 by RE or 64 by RE. Let's assume 16 by RE, right? Now you take actually the experimental reading. So in experimental reading, what you will get? You will get actually the flow rate, first thing. Second thing, you can also get the pressure drop, right? But in this experiment, I don't see actually, so we are not measuring the pressure drop. What we are doing, we are actually only measuring the flow rate. Is that correct actually, Mukesh? One minute, just hold on. Yes, Mukesh. Yeah. Mukesh, are you online?
Yes.
So we are only measuring the flow rate, right? And the Reynolds experiment. Okay, can you hear me?
Sir, we are measuring the flow rate in this experiment.
We are not measuring the pressure drop, right?
No, sir.
Okay, okay, that's fine. That's fine. So now we will come back to the error analysis, right? So now what we will do, we will actually, let's assume we are also measuring the pressure drop in the experiment. So now, in the same formula, whatever we have derived, we have one actually pressure drop using the Hagen-Pauli equation, right? For known flow rate, you can calculate the what is the pressure drop. So that you can use from there. From that calculation, you will get actually this friction factor that will be exactly falling on the line that is 16 by RE. Now, now we are using the same formula for friction factor. So what we need their pressure drop, right? And the flow rate to calculate the friction. Now what we will do, so now we got actually this pressure drop from experiments, right? Assume we have some pressure sensor at the inlet. So we exactly know actually that what is the pressure drop for given flow rate. So we will put that flow rate and pressure drop, and then we will calculate that will be our experimental friction factor. Now two things are there. We will get the same friction factor or close to that what we got actually what is called theoretically. Another thing is there because there is actually some error. So I can get higher friction this pressure drop, right? If higher pressure drop means I will get slightly higher this what is called friction factor, right? Although there is actually experimental reading, but it's a little bit off from our theoretical reading. So what we can do, we can take the difference of that. So let's take actually we have friction factor theoretical minus friction factor what is called experimental divided by our theoretical friction factor. So whatever error we will get, that how much actually it is off from the actual reading. So that is error analysis, right? So you can do actually that, and you can just find out the more the error will be, there are actually our readings are much more off from the actual reading. Or if the error is smaller, means our experiment observation is very close to the our theoretical prediction, right?
Excellent.
So that's the way actually you validate your, yeah.
So do we have to consider some sort of least count error? Because I don't think any least count was mentioned in the experiment. So do we have to consider like the least count of the instruments that are being used?
So least count actually in this, especially Reynolds experiment, right? You don't need that much actually. So normally what you are measuring the flow rate, right? So little bit here and there, you don't require. The least count actually, there are certain experiment where that matters a lot, but not in these experiments.
So sir, like for those experiments, would we be given the least count of the instruments in the videos, or can we assume?
I don't think actually in our videos we have given, but if you want to use actually in your theoretical part, it's up to you.
Fine, thank you, sir.
Yeah. And you can also do one thing actually. You can look at the effect of actually what is called your least count, that how much actually what is called error is accumulating for different least count, right?
Sure, sir. Sure, sir. So we can basically give it as a relative error in terms of
Yeah. You can run a simulation kind of thing, or you can make one case and study that we did this thing and this much error is accumulating, right? Just to find out the origin of error. Okay. Any other question? If there is no further question, then we can end this session, right?
Yes.
But before we end this session, there is just one thing. It is very important to visualize actually these experiments. Theory you have done pretty well in all the courses. I assume you have done actually like pretty well, and you understand these concepts in depth. But when it comes to designing the experiment and validating your model, it's a very difficult part. So just you have to put all your imagination in a very constructive manner and very focused manner when you are designing certain experiments. As I have given you one example, right? So I will just tell you a small story that will actually, so when you are doing this theoretical work, you are master of all these equations. Whatever you do, right? So all the outcome of your model are actually representation of your thought, whatever means you are thinking, right? But when you do the experiment, you get the data. That is not actually what you want. It is the way experiment behaves, right? So most of the time, what happens actually, our model is what is called predicting something else, but experiment is predicting entirely different. So now there are two things. One thing is whether our model is not correct. We have missed certain physics, or we have missed certain parameters. That is the one thing. Another thing is actually we have not designed our experiment actually in a very good manner, right? If your model is correct, if your experiment is also correct, you will get actually very good fit, and that's called the model validation, not experimental validation, right? So you don't validate the experiment, but what you do, you validate your model using experiment. So now I will tell you that small story. So during my PhD, actually, I was studying the same. So what I was studying the what is called this flow instability in flexible system. So we have already studied, right? Flow through pipe, flow through channel, flow through this tube. We have already studied. But now if I say that actually you have to study the flow in the flexible system, like the flexible system, like our arteries and veins, whether you will get the same actually laminar to turbulent transition at 2100 or not. That was the question. To answer that question, first you have to validate your system, right, with the pipe, that I have designed this experiment. Now I will get the same transition for a rigid tube at 2100. So we were doing the experiment, right? So we were repeating during day, and you won't believe the transition should take place at 2100. I was getting around 1200 transition laminar to turbulence, right? So now question is coming whether my experiment is wrong, or I've done some actually what is called missed some parameter in my calculation. But of course, the well established actually what is called principle that the transition takes place in tube around 2100, 100 here and 100 there. So approximate 1900 and 2200 somewhere the transition, but I'm getting at 1200. So what's the reason? So then we thought, what can be the reason? The reason is, the disturbance actually, external disturbance. So if we talk about the IIT, what is happening? There is actually these heavy trucks are going outside, right? These trains are moving. Even the planes, some kind of actually they create some vibration. You can feel inside the what is called our building here in labs, right? So then we thought actually means that is the actually problem that is pushing the transition from 2100 to 1200. But until we do the experiment, we don't know, right? So what we did, we waited actually. We waited like what is called like a 1 a.m. And during night when nobody is actually moving here and there, we performed our experiment. And you won't believe, we got it around like 2100. So the experimental setup is same, everything is same. We don't actually what is called included the external parameter. That was the vibration coming from different sources, right? So that was the case. That's the story actually. Sometimes your means experimental readings are entirely off from what you predict. So you have to also actually pinpoint that why it is happening. You have to understand your experiment. Now this is about 2100. Now if I will tell you that this turbulent what is called laminar to turbulent transition, that even don't take place at 2100. You can keep what is called keep this actually flow stable at Reynolds number around actually 100,000. Is that possible? So it is possible if you actually keep your these experiment on some table where there is no vibration, absolutely no vibration. You can maintain that thing, because what is happening, this small fluctuation in the system, those are triggering this laminar to turbulent transition, right? So people have done a lot of these mathematical study also that why this happens, and people have performed many experiments and they have found that actually you can delay this transition or postpone this transition. So there are a lot of literature, you can go through that, actually you will find very interesting thing. So that's the way we did. So that is about the rigid, actually what is called this tube. Then we perform the experiment with the flexible tube. So flexible tube, actually your what is called flow characteristic is entirely different than what is in rigid tube. right? So that actually, once you have validated your model, then what you can do, you can put another tube with the different shear modulus, you can run that experiment. And then you can observe how the flow characteristics are changing as a function of different parameter you have taken. Let's assume if I have taken the flexibility of the tube as a parameter, right? So those are the things actually one can do. Okay, so then I will stop. And so next, what is called doubt session will be on, I think, let me see the calendar, on 25th. And Professor Manoj will be taking that doubt session with. Okay.
Sir, I
Yes?
was saying something. Sir, sir, I am providing data for Reynolds operators because that was, I think, that was insufficient for.
You are, so please tell your name, Mukesh, right?
Yes, sir. Yes, sir.
Okay, yes, Mukesh, tell me.
Sir, I can provide the data for Reynolds operators, so they
Okay.
can write down, or
Okay,
or
okay. I think that's a great. If you can provide the data.
Okay, sir.
You can send me, I will upload actually on Moodle.
Sir, okay, sir, I can send.
Okay, okay. That's good. Thanks, Mukesh.
Also, sir, another request, if in the next video we could also have the slight theory behind why things are happening. That would be resourceful before, coming to the doubt session. Like if in the video, besides the procedure, if we have.
We have to modify the video, and means it takes a lot of time. What I can do actually, I will see actually if we can arrange something. But anyway, we will be discussing in the doubt session, so that's not a problem. You can go through the manual also. And if any what is called these online resource I will get, I will update that thing.
Sure, sir, sure, definitely.
Okay.
Yes.
Yeah. Okay.
Thank you.
But that's
Thank you,
not
sir.
a promise. I will try. Okay.
Sure, sir,
Yeah.
sure. Okay.
Okay. Good.
Okay, thank you, sir.
Okay, guys. So, any other question? If there is no question, thank you all. I can't offer you tea actually in online mode, but have a tea at home and enjoy. Okay. Okay. Thanks.
Thank you, sir.
Thank you, sir.
Yeah. Great.
So the last submission, this report submission is on Wednesday, right, sir? Next Wednesday,
Yes.
2 p.m.
Yes.
Okay, sir. Thank you,
So
sir.
don't delay it actually. Please don't miss. It looks little bit awkward, then people miss actually, and then they request. So please don't do that thing, right? Let's keep everything streamlined. So we actually submit our reports on time, and then we move ahead. Okay.
Yes, sir. Thank you, sir. Yes, sir.
Okay. Great.